Okay, let's unpack this. Have you ever looked at a property table, maybe for steam or a refrigerant, and just, taken for granted all those values for internal energy or entropy? We rely on them constantly in engineering and science, but here's the thing. You can't just stick a thermometer into a substance and read its entropy. So, how do scientists actually know these hidden properties? Today, we're taking a deep dive into the fascinating world of thermodynamic property relations. It's about revealing how we can determine properties that are, well, impossible to measure directly, all by using incredibly clever mathematical relationships derived from the ones we can measure, like temperature, pressure, and volume. It's like thermodynamic detective work.
It really is. And what's truly fascinating here is how seemingly abstract mathematical tools become unbelievably practical. Our mission today is to show you the fundamental connections that allow us to calculate these elusive properties. It's about turning what might seem like information overload into genuine aha moments, giving you a deeper appreciation for the very nature of matter and energy. You'll see how foundational concepts, maybe often intimidating at first glance, are actually the key to unlocking these profound secrets.
Okay, so if we can't directly measure properties like internal energy or entropy, where do we even begin this detective work?
Well, it all starts with a foundational principle. It's called the state
A
postulate.
state postulate, right?
Essentially, if you can nail down just two independent properties of a simple substance, let's say, its temperature and specific volume, you can, in theory, determine every single other property it possesses.
Just two properties define everything else. Okay.
That's the crucial starting point. But, this raises an important question. How do we mathematically describe how one property changes when multiple other properties are involved? This is where the power of partial derivatives comes in.
Partial derivatives. Okay.
Think of it this way. A simple derivative tells you how a function changes with respect to one variable. But a partial derivative, it shows how it changes when only one variable is allowed to vary while all the others are held constant.
Ah, I see. That's a crucial distinction. And what I find truly interesting here is the difference between partial and total differentials. A partial different, like the change in temperature with respect to pressure while holding volume constant, that just isolates one influence.
Right.
But the total differential for a property combines the influences of all variables changing simultaneously. It's like measuring the slope of a hill. A partial differential might tell you the slope if you only walk due north. The total differential tells you the slope no matter which direction you walk, factoring in all changes. Does that sound right?
Exactly. That's a great analogy. And this mathematical toolkit also includes powerful shortcuts. We rely on things like the reciprocity relation, which basically says the inverse of a partial derivative is equal to its reciprocal, a pretty neat flip.
Okay.
And then there's the cyclic relation, which links three partial derivatives in a beautiful loop. For example, for an ideal gas, we can actually prove this cyclic relationship means that if you multiply three specific partial derivatives together, the result is always -1.
-1.
It's a powerful self-consistency check for our thermodynamic models.
Those might sound a bit like academic exercises, but I see their utility.
Hmm.
So how do these tools translate into something we can use right away?
Yeah.
Can you give us an example of their immediate practical application?
Absolutely. You can use these fundamental mathematical tools to estimate real-world changes. Imagine you have air, which, for many engineering purposes acts like an ideal gas. If you know its initial temperature and specific volume, and then you have a small change in both, say, a tiny temperature bump from 300 Kelvin to 302 Kelvin and a slight volume increase, these principles allow you to estimate the resulting change in pressure with a remarkable accuracy.
So you can predict the pressure change.
Yes, like predicting a NATA 0.491 kps shift in a real scenario. It's about precisely predicting cause and effect. Very useful.
Okay, so we've armed ourselves with this mathematical toolkit for understanding how properties change. But what about those truly elusive properties, like entropy? How do engineers even begin to calculate something that can't be put on a gauge? This brings us to a set of relationships so elegant, they're named after a pioneering physicist, the Maxwell Relations.
Ah, the Maxwell Relations. This is where things get really profound for you, the listener. If we connect this to the bigger picture, these relations are derived from the four Gibbs equations.
Gibbs equations, okay.
These aren't just random formulas. They describe the fundamental energy changes in any system. Internal energy, enthalpy, the Helmholtz function, and the Gibbs function. Because these properties have what we call exact differentials, meaning their change depends only on the start and end points, not the path taken, it allows us to derive the Maxwell relations by equating cross derivatives.
Cross derivatives, okay.
It's a bit like knowing if you walk around a block, your net change in elevation is zero, no matter the specific path you take. These properties behave predictably.
That's a powerful idea, that these properties are so well behaved mathematically. So what does this actually mean for us as engineers trying to calculate the unmeasurable?
Well, these relations are incredibly valuable. Why? Because they provide a way to determine changes in entropy, which, as you pointed out, you absolutely cannot measure directly, simply by measuring changes in pressure, specific volume, and temperature, things we can measure. For example, one Maxwell relation tells us that the rate at which entropy changes with pressure at a constant temperature. Well, it's directly related to how specific volume changes with temperature at a constant pressure. This means we can infer entropy changes from data we can easily collect in a lab. It's the ultimate backdoor for design and analysis.
That sounds almost too good to be true. Are these theoretical connections actually verifiable in the real world?
They absolutely are. We
Yeah.
can take real data, say from steam tables at 250 degrees C and 300 kPa, and plug in the numbers to verify the Maxwell relations.
And they match up.
They do. Even though we're using finite values from tables instead of true infinitesimals, the calculated values typically come within, say, a few percent of each other. This close agreement gives us immense confidence in the fundamental principles behind these relations.
Speaking of real-world applications, one of the most practical applications stemming directly from the Maxwell relations is how we understand phase changes. Like how water boils or ice melts. This is where the truly powerful Clapeyron equation comes in. This equation is a thermodynamic superpower because it lets us figure out the enthalpy change during a phase transition just from pressure, volume, and temperature data.
That's the key. Before the Clapeyron equation, understanding phase changes often required complex calorimetric experiments. Imagine trying to measure the exact energy needed to boil a substance with a precise heat measurement setup. Really tricky stuff.
Right.
This equation, however, elegantly links the slope of the saturation curve on a PT diagram to the enthalpy of vaporization, that's the latent heat, the temperature, and the change in specific volume during the phase change. This means you don't need a calorimeter to find this crucial energy value. You just need easily measurable pressure, volume, and temperature data. It really democratized the understanding of phase transitions, enabling rapid design and innovation.
So you could, for instance, estimate the boiling temperature of a substance at a different pressure without having to run a whole new experiment.
Precisely. We can see this in action. If you know the heat and volume change when, say, 2 grams of liquid convert to vapor at 200 kPa and 80 degrees C,
Yeah.
the Clapeyron equation lets you accurately estimate the boiling temperature if the pressure drops to 180 kPa. The equation would tell you it's around 351.7 Kelvin, a precise prediction from simple measurable properties.
Wow, that's useful.
And for low pressures, there's an even simpler version, the Clapeyron-Clausius equation, which is incredibly useful for extrapolating tabular data. For example, estimating the saturation pressure of refrigerant 134A at Cagliari at 50 degrees F using data from negative 40 degrees F, well, it gives a value of 5.56 PA.
And how close is that?
What's remarkable is that this calculated value is typically only about 1% off the actual value for more detailed tables. It's an elegant approximation that saves immense experimental effort.
Okay, we've been diving into these specific relations, but now I want to zoom out a bit. If we know any two independent properties, we should, in theory, be able to calculate all others. So what are the universal equations that allow us to find changes in internal energy, enthalpy, and entropy applicable to any pure substance under any conditions?
That's an excellent next step. We can derive truly comprehensive formulas for calculating changes in internal energy, enthalpy, and entropy in terms of those easily measurable properties P, V, and T, along with the specific heats.
Right, specific heats too.
For instance, the change in internal energy can be found via a formula that factors in both the change in temperature and the change in volume, combined with a term that accounts for how pressure changes with temperature. It's like having a master key to unlock these properties for any substance.
And here's what I find a really cool insight from these general relations. The relationship between constant pressure specific heat, Cp, and constant volume specific heat, Cv. For ideal gases, we often treat them as having a simple constant difference. But for other substances, it's more complex, right?
It is, absolutely. And the Mayer relation beautifully quantifies this difference. This equation gives us a profound insight into why heating a substance at constant pressure always costs more energy than heating it at constant volume.
Why is that?
It's because at constant pressure, you're not just raising the temperature, you're also doing work to expand the substance against the surroundings.
Ah, the expansion work.
Exactly. This elegant equation precisely quantifies that extra energy requirement using a substance's fundamental properties, like how much it expands its volume expansivity and how much it compresses its isothermal compressibility.
Uh,
And this relationship leads to some critical conclusions. Cp is always greater than or equal to Cv.
Always.
Always. Their difference approaches zero as absolute temperature approaches zero, a very interesting quantum effect, actually. And for nearly incompressible substances like liquids and solids, they are essentially identical. Makes sense, right? They don't expand much.
Right, negligible expansion work.
And for an ideal gas, this complex relation elegantly simplifies to the familiar equation. Cp minus Cv simply equals R, the gas constant. It connects the abstract to the everyday.
That's neat how it simplifies. Okay, now, have you ever noticed how refrigerators work? Or maybe why a compressed gas tank feels icy cold when you release the gas quickly? That feeling of cold is often due to a process called throttling. And our guide to understanding exactly what happens to a fluid's temperature during such a process is something called the Joule-Thomson Coefficient. What exactly is it telling us?
Right, the Joule-Thomson Coefficient, often written as μJT, it's essentially a measure of how much a fluid's temperature changes for a given change in pressure during a constant enthalpy process.
Constant enthalpy. So total energy flow stays the same.
Correct. A process where the total energy of the flow remains constant, like flowing through a valve or a porous plug. Now, if this coefficient is positive, the temperature decreases during throttling. That's exactly what we want for cooling applications, like in your fridge.
Okay, positive means cooling.
Yes. If it's negative, the temperature actually increases. And if it's zero, the temperature stays constant. It's a critical design parameter for refrigeration and liquefaction systems.
So on a simple temperature-pressure diagram,
Right.
you can visualize this by looking at constant enthalpy lines, where their slope is equal to this coefficient. But I've heard there's an inversion line where things get really interesting for cooling. Can you explain that?
Yes, the inversion line. It's a curve on the TTP diagram where the Joule-Thomson coefficient is exactly zero. This line separates regions where throttling causes cooling from regions where it causes heating. For a cooling effect, the fluid must be throttled on the left side of this inversion line, in the region where μJT is positive.
Left side for cooling. Got it.
This means it needs to be below its maximum inversion temperature. For example, hydrogen. Its maximum inversion temperature is a very chilly -68 degrees C.
Minus 68 C.
Right. So if you want to cool hydrogen by throttling, you first have to pre-cool it below that temperature. Otherwise, if you throttle it from room temperature, it will just get warmer.
Wow, okay. That's counterintuitive unless you know about the inversion line.
Exactly. And here's a crucial takeaway. For an ideal gas, the Joule-Thomson coefficient is always zero.
Always zero for ideal gases. Why?
Because the enthalpy of an ideal gas depends only on its temperature, not its pressure or volume. Remember that.
Right. Enthalpy is just a function of T for ideal gases.
Precisely. Therefore, if the enthalpy remains constant during a throttling process, which it does by definition, the temperature of an ideal gas must also remain constant. So, you simply can't cool an ideal gas by throttling it. That's a fundamental difference between ideal and real gases.
That's a very clear distinction. So far, many of our relations assume ideal gas behavior, which is fantastic for low pressures, simplifies things. But what about real gases substances like high-pressure natural gas or refrigerants where they start to act? Well, less than ideal. The ideal gas law just doesn't cut it anymore at high pressures.
That's a vital point, and it's where much of real-world engineering happens. At high pressures or near their critical points, gases deviate significantly from ideal behavior. Those simple relations aren't accurate enough. This is where generalized charts come in. They're really a stroke of genius for practical engineering.
Generalized charts, what are they?
These charts, like the enthalpy departure chart or the entropy departure chart, allow us to account for these deviations. They do it by normalizing a substance's properties against its critical point.
The critical point. That unique state where liquid and gas phases become indistinguishable.
Exactly. It acts as a kind of universal reference state.
So if I'm understanding correctly, these charts allow us to use a single set of graphs to correct calculations for many different real gases just by knowing how close they are to this critical point, using something called reduced properties.
Exactly. It's an incredibly powerful concept. It means we can still calculate changes in enthalpy, internal energy, and entropy for real gases, but we adjust the ideal gas values. We use enthalpy departure factors and entropy departure factors read from these charts to make precise corrections.
So you calculate the ideal change, then add a correction.
Pretty much. The change in enthalpy of a real gas, for example, isn't just the ideal change. It's that ideal value minus a correction term derived from the charts, factoring in how non-ideal it truly is based on its reduced temperature and pressure.
Okay, that makes sense. You start ideal, then correct for reality.
You got it. And you can see the significant impact of this in real-world scenarios. Consider compressing propane isothermally constant temperature from, say, 200 psia up to 800 psia at 200 degrees F.
Okay, high pressure propane.
If we were to just assume ideal gas behavior, we would make huge errors in calculating the work needed and the heat removed. But by using these generalized charts for real gas behavior, we get a much more accurate heat rejection value, something like 140.6 BTU per pound mass.
And the ideal gas assumption.
If we had just assumed ideal gas, we would have dramatically underestimated both the boundary work required by about 9% and the actual heat transfer needed by a whopping 71%.
71%, yeah.
This vividly demonstrates why these charts are indispensable for accurate, real-world engineering calculations. You ignore the real gas effects at your peril in many cases.
Absolutely. Well, from the elegant simplicity of partial derivatives to the practical power of generalized charts, we've really taken a deep dive into how engineers and scientists unravel the hidden properties of matter. It's been a journey from the theoretical underpinnings to the intensely practical applications, showing how seemingly abstract mathematical tools provide concrete answers about the substances that, well, power our world.
It's quite a story, isn't it? You've seen how the exactness of thermodynamic differentials leads to fundamental relationships like the Maxwell relations, allowing us to essentially measure the unmeasurable, like entropy changes. The Clapeyron equation, in turn, provides a clever and incredibly efficient way to determine phase change enthalpies from simple PVT data bypassing complex experiments. And the Joule-Thomson Coefficient gives us the precise understanding needed to design effective cooling processes. While for real gases, those generalized charts are absolutely indispensable, providing accuracy where ideal gas models just completely fail.
So next time you glance at a property table or think about a fluid changing temperature in an engine or a refrigerator, maybe consider the intricate web of thermodynamic relations at play behind the scenes. This knowledge isn't just for textbooks. It's really the bedrock of countless technologies you interact with every single day, quietly working to make our modern world function.
It really is fundamental, and this raises an important question for you to ponder.
Yeah.
Given the incredible power of these fundamental relations to predict properties we can't directly measure, well, how might future technologies exploit new, perhaps even currently unimagined properties? What if we could just find the right two independent variables and their elegant partial derivative relationships? What secrets are still waiting to be unlocked by applying these principles in new ways?